In this lesson, we will learn about compound inequalities and how that extends to absolute value inequalities. Compound inequalities break down into two categories, conjunction and disjunction. Looking at conjunction first, con meaning with, we want to take the intersection or overlap of the sets as the solution. So in other words, conjunction means and therefore you must include the values that satisfy both inequalities at the same time. So here are the three steps. You solve if needed, graph the inequalities on the number line, and wherever they overlap, that is the solution. And don't forget to write the answer as a compound inequality. In the first problem, we're going to solve, writing the answer as a compound inequality, and then we'll graph the solution on the number line. So in this inequality, we want to add 1 to both sides. And in the second inequality, we want to divide both sides by 2. What we have is a complete mathematical sentence. However, there is a more concise way to write it by combining the two inequalities, writing the numbers numerically from left to right on the number line as follows. If that solution came as a surprise, let me break it down. So the values of x that make both inequalities true at the same time are x less than -4 because, let's say I have -5. That would be less than -4 and less than or equal to +5. But if I chose, say, 4, that would satisfy this inequality but not this one. To visually represent that, we can graph the solution on the number line first and then deduce what the final inequality will be. When I do this, I want to write each inequality separately, stacked vertically, as follows. Now we can see that there is overlap here if I were to combine these two graphs. And that's why x less than -4 is the answer. So this is a compound inequalities, that's specifically a conjunction, and that was explicitly told to us because of the word and that joined these two inequalities, and therefore you are looking for the intersection. Always know ahead of time before you start solving your inequalities if you're working with a conjunction or disjunction so that you know how to properly interpret the result. In this example, we are presented with a concise version of a and compound inequality, a conjunction. So the shortcut here is to add 2 to all parts and then carry all 3 down. So we will have 12 is less than or equal to 3y is less than to 21. Divide everything by 3. So then 4 is less than or equal to y is less than or equal to 21/4. 7. And doing the problem that way saves a lot of effort. So this is an and compound inequality because the y is in between two inequalities and it is read with y as the subject. So y is greater than or equal to 4 and y is less than 7. That's how it is read. And then we graph this on the number line. And y is physically between the 4 and the 7, where we use a closed dot to show inclusion of the 4 and an open circle to show that 7 is a boundary that is not included. So this is our correct writing of the compound and inequality, the conjunction, and this is the correct graph on the number line. Moving now to disjunction, so separate or union, so you just take everything. It doesn't have to overlap. And this is going to be tipped off using the word or, and now as long as the values satisfy one or the other or both, you include that in the solution. So here we want to do the same thing. And this one's already done for us. So here in the second inequality, we will subtract 4 and divide by 2. Now because with OR, we can't write our inequalities in a combined fashion, so we just have to write the following. We use the word OR to join the two parts of the disjunction, and please make sure that you write the one on the left that refers to the less than or equal to. So this 5 comes first on the number line from left to right, and then or z is greater than 8. Let's graph this. So I set up 3 vertical number lines. The first one will be z is less than or equal to -5. The second one will be z is less than 8. So then I could clearly see how I'm supposed to take the union or everything and merge that onto my answer one. This is only to help. This is not required. If you are able to go right to the answer, that is fine. So we have the union of these two provides this number line as the answer because it is a disjunction. So it could be 4, so it could satisfy this, or it could be 9 and satisfy this. It's one or the other, and so that means it's part of the answer. We have taken a look at conjunction, so and disjunction, or, and now we are going to apply it to absolute value, which adds a couple layers. We'll first start with equations, and then we'll move to inequalities. So the definition of absolute value is as follows. But first understand that absolute value is simply the distance from 0. It's a definition. So we have the absolute value of A is equal to B implies the following two results. First, the positive case, A equals B. So if we take the absolute value of 3, well, that equals 3. And the second result is the negative case, that the negative of A is equal to B. So if I take the absolute value of -3, let's say that's my A value. So now if I do the negative of -3, that will also equal to 3 from up here, because the distance of 3 from 0 on the number line is 3, where distance is always positive and negative only infers direction. So this is the definition of absolute value that you need to commit to memory. So you always need to account for the fact that A could have been positive or the fact that A could have been negative. So you do have to make 2 equations because algebra is about finding all of the unknowns. A few things to keep in mind. So you want to account for the possibility that you took the absolute value of a negative, and you want to isolate the absolute value before creating the positive and negative cases, because in this definition, it's the absolute value of some amount. So in this case, I would want to divide that 2 over first, and then I could apply the definition of absolute value, creating the positive and the negative cases. Here, I need to add 6 to both sides before I could then branch off and make my 2 parts. Now, you want to avoid multiplying or dividing into or out of the absolute value symbols. They are grouping symbols, but they are not parentheses. They represent a definition saying that this quantity's distance from 0. This quantity's distance from 0. And since this is the definition where the absolute value is isolated, you have to, oh, sorry, I got a little confused. So here, it is distance from 0, so you have to first apply the definition, making your positive and negative cases, before you can then extract whatever is inside and continue to isolate your unknown. The fourth part is not just busy work. You have to check your answers. You might create what's called an extraneous solution. Because you're creating additional copies of your equation and changing values, you might end up with something that is not part of the original solution, hence extraneous. Now, sometimes you could see that ahead of time, and then you could call the equations bluff. Sometimes it might have no solution, and that would be when an absolute value equals a negative, and then you wouldn't have to do any work. So let's solve the first 2 examples. As I mentioned earlier, the first step is to isolate the absolute value by dividing the 2 to the other side. A couple notes: you can never distribute into an absolute value. You can never subtract out of an absolute value. You have to isolate first and then apply the definition with the positive and negative cases. Now, a couple other things. Notice that this -3 stuck around inside the absolute value. It does not spontaneously become a positive. That's not what absolute value does. I know it always equals a positive by definition, but it's the distance from 0 of this quantity. So what is really happening is you never just change that to a positive. And the reason why I switched the order of this is because I need a minus anyway to represent this quantity, so I might as well take out the plus, because that minus operator will join the two. So the next step is to apply the definition, creating the positive and negative cases. So now I am finding out that this quantity here has a distance of 5 on the right side of the number line from 0, and this quantity here has the distance from 0 on the left side. Now, you might try to call me out and say that I put the negative on the wrong side, because by definition I'm saying that the inside could have been positive or negative before taking the absolute value. Now, as long as you negate one side, that is equivalent to negating the other side by the symmetric property of equality, or the reflexive property of equality. So it's a lot easier just to negate one term than it is to distribute and negate the k minus 3 term. So typically you will see me negate the right hand side. So then you solve each of these, getting k equals 8 and k equals -2, and I really want to box the answers because I've isolated the possible values of the variable, but I have to check in case I made an extraneous solution, which usually with these problems will only happen if there wasn't a solution to begin with, which you'd be able to tell right here, because the absolute value, if it equaled a negative, you could then say there was no solution. But as you could tell, if you check, you can go back to the original, or you could go back to the isolated absolute value, because that's the time before you made it an extra copy of the equation. So 8 minus 3 is 5, and -2 minus 3 is -5. Absolute value, or distance from 0, is 5. So both of these work. So we box both of them to clearly represent our answer. In the next problem, we start off by adding 6 to both sides. Now that's a good thing because we have an absolute value and the other side is a negative, but you have to isolate first before you can judge the situation properly. The absolute value is equal to a positive, so we're looking good. And now with the absolute value isolated, we branch into the positive and negative cases. So we have the positive case, no sign changes, no longer including the absolute value symbol because we have applied its definition, so we've created its equivalent two cases that it represents, and then here the negative. If we are dividing by 4 on the left of an equation, that means we're multiplying by 4 on the right, producing the following. And after we check, remember we don't have to go all the way to the top because there are some unsimplified algebraic manipulations, so instead we go here before we apply the definition where the extraneous solutions can come in. And 16 on 4 is 4, and negative 16 on 4 is -4. Absolute value, or distance from 0, is 4. So both of these are correct. The last part of the lesson is the hardest because it is going to tie in everything that we've learned with absolute value and inequalities. With inequalities and negatives, you have to change the direction of the inequality when you multiply or divide by negative, which is what you do when you apply the definition of absolute value when you handle the negative case. So you need to learn whether an absolute value inequality is a conjunction and intersection, or a disjunction, or a union. So consider the following. If you have isolated the absolute value, and it contains an unknown, and it is greater than or equal to, it's the direction that matters here, a positive number, then it is going to be an or, because think about that. I could choose values of x such as 4, 5, -7, 8, -9, but notice I can't get anything in between 3 or -3, and the betweenness is the overlap or the and. So notice I can only make two wings that go out in either direction on the number line after 3 or -3. Let me show you how this simplifies once we apply the definition of absolute value. So we have the positive case, which is the identical but without the absolute value symbol. because we've accounted for the negative case here. And notice in the different color, what's changed from the original is the direction of the inequality and the sign of that term. And like I said, it's just usually easier to negate the right-hand side because it's typically one term. And this is going to be an or compound inequality, a disjunction. That's because if you graph this on the number line, you're going to see two separate branches like the following. So as long as we are greater than 3 or less than negative 3, this absolute value inequality is true. And that is when an unknown is an absolute value and the inequality is greater than some positive number. Now, if it's the reverse, if you're containing an unknown and an absolute value and it's less than or equal to some positive number, then that is an and compound inequality, a conjunction. But be very clear that it's only after you isolate the absolute value then you know that the inequality with respect to the unknown has the proper relationship, and of course we're always writing the unknown first on the left of the inequality. Applying the definition of absolute value gives the following. The positive case, remove the absolute value, and then the negative case showing what changed in orange. So we changed the direction of the inequality because we negated one of the sides, which is like dividing by a negative. Let's take a look at the graph here, realizing that the x is kind of wedged by that 3 because it's 3 or negative 3, so it can't escape them. So I could have a 0, a negative 1, a 1, a 2, a negative 2, a 3, a negative 3. So that is the overlap. So that's kind of the intuition you need when looking at this to decide that is a conjunction. Graphically, we get the following. And as you can see, we are overlapped, so that is conjunction. So note the following. We will change the direction of the inequality when creating the negative case of absolute value. Do not forget to do that. So we are going to solve and write our answers as compound inequalities, graphing them on the number line. Now, if it helps you, you can solve, and then before making a compound inequality, you can graph the solution on the number line and decide what you want to do. But either way, with absolute value inequalities, you must decide, once you get the absolute value isolated, if you have a disjunction or a conjunction, so then you know how to interpret the result, because there are special cases where it's no solution or the set of reals, and if you don't know what type of compound inequality you have, you won't make the right choice 50% of the time. In this first example, dividing by 3 on the left is multiplying by 3 on the right. With the absolute value isolated, I can now tell that because it's the unknown in the absolute value less than 3, then this is an and inequality. That is a trick to remember it. It's not mathematical, but use it if you need to. Less than or equal to 3. So this is an and. So let me identify that. An and, by the way, has this symbol. So now I apply the definition of absolute value to find the distance from 0. For emphasis, I have shown that the inequality direction and the sign of the right-hand side is changed. And now I solve each of these by subtracting 7 and then dividing by 2. Now here I'm dividing by positive 2, so even though that is dividing into a negative, the divisor itself wasn't negative, so the inequality doesn't change. And so we get the following. Because this is and, I need overlap. So x is less than or equal to negative 2. X is greater than or equal to negative 5. That's good news, because if you start at negative 5 and go right, greater than, that is going to overlap with starting at negative 2, and since this is less than, going to the left. Let's see that graphically. So I took the liberty to show us the first inequality, the second inequality, and then how they overlap. So this is the answer graphed on the number line, and I still need to write this as a compound in a concise form as follows. And doing the graphing first helps me visually see that I need the negative 5 first, the negative 2 second, because it's always numerical order, and then x is in the middle where it's shaded. So this is read as x as the subject. X is greater than or equal to negative 5, and x is less than or equal to negative 2. In the next problem, I have to start by adding 3, and then I'll consider if I have a disjunction or a conjunction. And notice what I stumble upon, that an absolute value is greater than a negative always. So I know that the answer is a set of reals right now, but I still want to go through this problem in case you missed that. I want to show you how you can then get to the correct answer at the end. So what I need to do here is consider and or. Well, it's greater than, so it's an or, and so feel free to use that trick, but the math of it is what I explained up here. So it could be -4 or 4 or 5 or -5, 6 or -6, etc. So it's going away from one another, and this is enclosing it. So that's the overlap. So going in, I know that this needs to be an or compound inequality, which has the union symbol as follows there. So I will now apply the definition of absolute value. And again, for emphasis, I showed what changed with the negative case, both the inequalities direction and the sign of that side. If I'm dividing by 2 on the left, that means I'm multiplying by 2 on the right because that's the inverse operation. And I will now put these on 3 separate number lines looking to take the union. And what you'll notice is that everything is covered from here to there and from over there to there. There's overlap here especially. But since this is the union or, I have to take this as well as this and put it here, covering the entire number line. And therefore, R is the set of real numbers. And if I thought that from this result I was supposed to use a conjunction, then I might have only taken the intersection. So know ahead of time, after you isolate the absolute value, if it's greater than, greater, so that's a union, and if it's isolated absolute value and it's less than or equal to, then less than is and, so it's conjunction, and I need to have the intersection or the in-between.